ASCII, Wikipedia article audio. ASCII 6 abbreviated from American Standard Code for Information Interchange, is a character encoding standard for electronic communication. ASCII codes represent text in computers, telecommunications equipment, and other devices. Most modern character encoding schemes are based on ASCII, although they support many additional characters. ASCII is the traditional name for the encoding system. The Internet Assigned Numbers Authority prefers the updated name ASCII, which clarifies that this system was developed in the US and based on the typographical symbols predominantly in use there. Overview. History. ASCII is one of a 1963 list of IEEE milestones. ASCII was developed from telegraph code. Its first commercial use was as a 7-bit teleprinter code promoted by Bell Data Services. Work on the ASCII standard began on October 6, 1960, with the first meeting of the American Standards Association SX 3.2 subcommittee. The first edition of the standard was published in 1963, underwent a major revision during 1967, and experienced its most recent update during 1986. Compared to earlier telegraph codes, the proposed Bell code and ASCII were both ordered for more convenient sorting of lists, and added features for devices other than teleprinters. Originally based on the English alphabet, ASCII encodes 128 specified characters into 7-bit integers as shown by the ASCII chart above. 95 of the encoded characters are printable. These include the digits 0 to 9, lowercase letters A to Z, uppercase letters A to Z, and punctuation symbols. In addition, the original ASCII specification included 33 non-printing control codes which originated with teletype machines. Most of these are now obsolete. For example, lowercase I would be represented in the ASCII encoding by binary 110, 1001 equals hexadecimal 69 equals decimal 105. The American Standard Code for Information Interchange was developed under the auspices of a committee of the American Standards Association, called the X3 Committee, by its X3.2 subcommittee, and later by that subcommittee's X3.2.4 working group. The ASA became the United States of America Standards Institute, 211 and ultimately the American National Standards Institute. Design considerations. With the other special characters and control codes filled in, ASCII was published as ASA X 3.4-1963, leaving 28 code positions without any assigned meaning, reserved for future standardization, and one unassigned control code, 66, 245. There was some debate at the time whether there should be more control characters rather than the lowercase alphabet, 435. The indecision did not last long. During May 1963, the CCITT Working Party on the new telegraph alphabet proposed to assign lowercase characters to sticks 6 and 7. An international organization for standardization TC97SC2 voted during October to incorporate the change into its draft standard. The X 3.2.4 task group voted its approval for the change to ASCII at its May 1963 meeting. Locating the lowercase letters in sticks 6 and 7 caused the characters to differ in bit pattern from the uppercase by a single bit, which simplified case-insensitive character matching and the construction of keyboards and printers. The X3 committee made other changes, including other new characters, renaming some control characters and moving or removing others, 247-248 ASCII was subsequently updated as USASX 3.4-1967, then USASX 3.4-1968, ANSI X 3.4-1977, and finally, ANSI X 3.4-1986. Bit width. Revisions of the ASCII standard. In the X 3.15 standard, the X3 committee also addressed how ASCII should be transmitted, 249-253, and how it should be recorded on perforated tape. They proposed a 9-track standard for magnetic tape, and attempted to deal with some punched card formats. The X 3.2 subcommittee designed ASCII based on the earlier teleprinter encoding systems. Like other character encodings, ASCII specifies a correspondence between digital bit patterns and character symbols. This allows digital devices to communicate with each other and to process, store, and communicate character-oriented information such as written language. Before ASCII was developed, the encodings in use included 26 alphabetic characters, 10 numerical digits, and from 11 to 25 special graphic symbols. To include all these, and control characters compatible with the Comite Consultatif International Telephonique et Télégraphique International Telegraph Alphabet No. 2 Standard of 1924, Field Data, and early ASCII, more than 64 codes were required for ASCII. Internal organization. ITA2 were in turn based on the 5-bit telegraph code Émile Baudot invented in 1870 and patented in 1874. Character order. The committee debated the possibility of a shift function, which would allow more than 64 codes to be represented by a 6-bit code. In a shifted code, some character codes determine choices between options for the following character codes. It allows compact encoding, but is less reliable for data transmission, as an error in transmitting the shift code typically makes a long part of the transmission unreadable. The Standards Committee decided against shifting, and so ASCII required at least a 7-bit code, 215, 236-4. Character groups. The committee considered an 8-bit code, since 8 bits would allow two 4-bit patterns to efficiently encode 2 digits with binary-coded decimal. However, it would require all data transmission to send 8 bits when 7 could suffice. The committee voted to use a 7-bit code to minimize costs associated with data transmission. Since perforated tape at the time could record 8 bits in one position, it also allowed for a parity bit for error checking if desired. 217, 236 8-bit machines that did not use parity checking typically set the 8th bit to 0. In some printers, the high bit was used to enable italics printing. The code itself was patterned so that most control codes were together and all graphic codes were together, for ease of identification. The first 2 so-called ASCII sticks were reserved for control characters, 220, 236 8,9. The space character had to come before graphics to make sorting easier, so it became position 20 hex, 23710. For the same reason, many special signs commonly used as separators were placed before digits. The committee decided it was important to support uppercase 64-character alphabets, and chose to pattern ASCII so it could be reduced easily to a usable 64-character set of graphic codes, 228, 237-14, as was done in the DIS 6-bit code. Lowercase letters were therefore not interleaved with uppercase. To keep options available for lowercase letters and other graphics, the special and numeric codes were arranged before the letters, and the letter A was placed in position 41 hex to match the draft of the corresponding British Standard, 23818. The digits 09 are prefixed with 011, but the remaining 4 bits correspond to their respective values in binary, making conversion with binary-coded decimal straightforward. Control characters. Many of the non-alphanumeric characters were positioned to correspond to their shifted position on typewriters. An important subtlety is that these were based on mechanical typewriters, not electric typewriters. Mechanical typewriters followed the standard set by the Remington No. 2, the first typewriter with a shift key, and the shifted values of 2, 3, 4, 5, 6, 7, 8, 9 were numbered %, and early typewriters omitted 0 and 1, using O and L instead, but 1 and 0 pairs became standard once 0 and 1 became common. Thus, in ASCII, number $% were placed in the second stick, positions 1-5, corresponding to the digits 1-5 in the adjacent stick. The parentheses could not correspond to 9 and 0, however, because the place corresponding to 0 was taken by the space character. This was accommodated by removing from 6 and shifting the remaining characters, which corresponded to many European typewriters that placed the parentheses with 8 and 9. This discrepancy from typewriters led to bit-paired keyboards, notably the Teletype Model 33, which used the left-shifted layout corresponding to ASCII, not to traditional mechanical typewriters. Electric typewriters, notably the IBM Selectric, used a somewhat different layout that has become standard on computers following the IBM PC, especially Model M, and thus shift values for symbols on modern keyboards do not correspond as closely to the ASCII table as earlier keyboards did. The slash pair also dates to the number 2, and the pairs were used on some keyboards so they could be used in uppercase without unshifting. However, ASCII split the pair and rearranged mathematical symbols to asterisk, plus equals. Some common characters were not included, notably 1/2, 1/4 cent, while were included as diacritics for international use, and for mathematical use, together with the simple line characters \. The @ symbol was not used in continental Europe, and the committee expected it would be replaced by an accented A in the French variation, so the @ was placed in position 40 hex, right before the letter A, 243. The control codes felt essential for data transmission were the start of message, end of address, end of message, end of transmission, who are you, a reserved device control, synchronous idle, and acknowledge. These were positioned to maximize the Hamming distance between their bit patterns, 243-245. ASCII code order is also called ASCII alphabetical order. Collation of data is sometimes done in this order rather than standard alphabetical order. The main deviations in ASCII order are: an intermediate order converts uppercase letters to lowercase before comparing ASCII values. Printable characters. ASCII reserves the first 32 codes for control characters, codes originally intended not to represent printable information, but rather to control devices that make use of ASCII, or to provide meta-information about data streams such as those stored on magnetic tape. Character set. For example, character 10 represents the line feed function, and character 8 represents backspace. RFC 2822 refers to control characters that do not include carriage return, line feed, or whitespace as non-whitespace control characters. Except for the control characters that prescribe elementary line-oriented formatting, ASCII does not define any mechanism for describing the structure or appearance of text within a document. Other schemes, such as markup languages, address page, and document layout and formatting. ASCII 3.4-1963, ASCII 3.4-1965, 423, 425-428, 435-439, USASX 3.4-1967, USASX 3.4-1968, ANSI X 3.4-1977, ANSI X 3.4-1986, ANSI X 3.4-1986, ANSI X 3.4-1986, ANSI INSITS 4-1986, ANSI INSITS 4-1986, ANSI INSITS April 1986. The original ASCII standard used only short descriptive phrases for each control character. The ambiguity this caused was sometimes intentional, for example where a character would be used slightly differently on a terminal link than on a data stream, and sometimes accidental, for example with the meaning of delete. Probably the most influential single device on the interpretation of these characters was the teletype Model 33 ASR, which was a printing terminal with an available paper tape reader/punch option. Paper tape was a very popular medium for long-term program storage until the 1980s, less costly and in some ways less fragile than magnetic tape. In particular, the teletype Model 33 machine assignments for codes 17, 19, and 127 became de facto standards. The Model 33 was also notable for taking the description of Control G literally, as the unit contained an actual bell which it rang when it received a bell character. Because the keytop for the O key also showed a left arrow symbol, a non-compliant use of code 15 interpreted as delete previous character was also adopted by many early time-sharing systems but eventually became neglected. All uppercase come before lowercase letters, for example, Z precedes A, digits and many punctuation marks come before letters. When a teletype 33 ASR equipped with the automatic paper tape reader received a Control S, it caused the tape reader to stop. Receiving Control Q caused the tape reader to resume. This technique became adopted by several early computer operating systems as a handshaking signal warning a sender to stop transmission because of impending overflow. It persists to this day in many systems as a manual output control technique. On some systems Control S retains its meaning but Control Q is replaced by a second Control S to resume output. The 33 ASR also could be configured to employ Control R and Control T to start and stop the tape punch. On some units equipped with this function, the corresponding control character lettering on the keycap above the letter was tape and tape respectively. Use. Variants and derivations. 7-bit codes. 8-bit codes. Code 127 is officially named delete but the teletype label was rub out. Since the original standard did not give detailed interpretation for most control codes, interpretations of this code varied. The original teletype meaning, and the intent of the standard, was to make it an ignored character, the same as null. This was useful specifically for paper tape, because punching the all ones bit pattern on top of an existing mark would obliterate it. Tapes designed to be hand-edited could even be produced with spaces of extra nulls so that a block of characters could be rubbed out and then replacements put into the empty space. Some software assigned special meanings to ASCII characters sent to the software from the terminal. Operating systems from Digital Equipment Corporation, for example, interpreted del as an input character as meaning remove previously typed input character, and this interpretation also became common in Unix systems. Most other systems used BS for that meaning and used del to mean remove the character at the cursor. That latter interpretation is the most common now. Many more of the control codes have been given meanings quite different from their original ones. The escape character, for example, was intended originally to allow sending other control characters as literals instead of invoking their meaning. This is the same meaning of escape encountered in URL encodings, C language strings, and other systems where certain characters have a reserved meaning. Over time this meaning has been co-opted and has eventually been changed. In modern use, an ASCII sent to the terminal usually indicates the start of a command sequence, usually in the form of a so-called ANSI escape code from ECMA 48 and its successors, beginning with ASCII followed by a character. An ASCII sent from the terminal is most often used as an out-of-band character used to terminate an operation, as in the TICO and 6 text editors. In graphical user interface and windowing systems, ASCII generally causes an application to abort its current operation or to exit altogether. The inherent ambiguity of many control characters, combined with their historical usage, created problems when transferring plain text files between systems. The best example of this is the new line problem on various operating systems. Teletype machines required that a line of text be terminated with both carriage return and line feed. The name carriage return comes from the fact that on a manual typewriter the carriage holding the paper moved while the position where the type bars struck the ribbon remained stationary. The entire carriage had to be pushed to the right in order to position the left margin of the paper for the next line. DIS operating systems used both characters to mark the end of a line so that the console device would work. By the time so-called glass TTYs came along, the convention was so well established that backward compatibility necessitated continuing the convention. When Gary Kildall created CP/M, he was inspired by some command line interface conventions used in DIS SRT11. Until the introduction of PC-DOS in 1981, IBM had no hand in this because their 1970s operating systems used EBCDIC instead of ASCII, and they were oriented toward punch card input and line printer output, on which the concept of carriage return was meaningless. IBM's PC-DOS inherited the convention by virtue of being a clone of CP/M, and Windows inherited it from MS-DOS. Unfortunately, requiring 2 characters to mark the end of a line introduces unnecessary complexity and questions as to how to interpret each character when encountered alone. To simplify matters, plain text data streams, including files, on Multics used line feed alone as a line terminator. Unix and Unix-like systems, and Amiga systems, adopted this convention from Multics. The original Macintosh OS, Apple DOS, and Pro DOS, on the other hand, used carriage return alone as a line terminator. However, since Apple replaced these operating systems with the Unix-based Mac OS operating system, they now use line feed as well. The Radio Shack TRS-80 also used a lone CR to terminate lines. Computers attached to the ARPANET included machines running operating systems such as TOPS 10 and 10X using CRLF line endings, machines running operating systems such as Multics using LF line endings, and machines running operating systems such as OS/360 that represented lines as a character count followed by the characters of the line and that used EBCDIC rather than ASCII. The Telnet protocol defined an ASCII network virtual terminal, so that connections between hosts with different line ending conventions and character sets could be supported by transmitting a standard text format over the network. Telnet used ASCII along with CRLF line endings, and software using other conventions would translate between the local conventions and the NVT. The File Transfer Protocol adopted the Telnet protocol, including use of the Network Virtual Terminal, for use when transmitting commands and transferring data in the default ASCII mode. This adds complexity to implementations of those protocols, and to other network protocols, such as those used for email and the World Wide Web, on systems not using the NVT CRLF line ending convention. Unicode. The PDP-6 monitor, and its PDP-10 successor TOPS 10, used Ctrl-Z as an end-of-file indication for input from a terminal. Some older operating systems, such as CP/M, tracked file length only in units of disk blocks and used Ctrl-Z to mark the end of the actual text in the file. For these reasons, EOF, or end of file, was used colloquially and conventionally as a three-letter acronym for Ctrl-Z instead of substitute. The end of text code, also known as Ctrl-C, was inappropriate for a variety of reasons, while using Z as the control code to end a file is analogous to it ending the alphabet and serves as a very convenient mnemonic aid. A historically common and still prevalent convention uses the ETX code convention to interrupt and halt a program via an input data stream, usually from a keyboard. In C library and Unix conventions, the null character is used to terminate text strings. Such null-terminated strings can be known in abbreviation as ASCIIs or ASCIIs, where here Z stands for 0. Other representations might be used by specialist equipment, for example ISO 2047 graphics or hexadecimal numbers. Notes. Codes 20 hex to 70 hex, known as the printable characters, represent letters, digits, punctuation marks, and a few miscellaneous symbols. There are 95 printable characters in total. Code 20 hex, the space character, denotes the space between words, as produced by the space bar of a keyboard. Since the space character is considered an invisible graphic, 223 it is listed in the table below instead of in the previous section. Code 7F hex corresponds to the non-printable delete control character and is therefore omitted from this chart. It is covered in the previous section's chart. Earlier versions of ASCII used the up arrow instead of the caret and the left arrow instead of the underscore. Legend. ASCII was first used commercially during 1963 as a 7-bit teleprinter code for American Telephone and Telegraph's TWX network. TWX originally used the earlier 5-bit ITA2, which was also used by the competing Telex teleprinter system. Bob Bemer introduced features such as the escape sequence. His British colleague Hugh MacGregor Ross helped to popularize this work according to Bemer, so much so that the code that was to become ASCII was first called the Bemer-Ross code in Europe. Because of his extensive work on ASCII, Bemer has been called the father of ASCII. On March 11, 1968, U.S. President Lyndon B. Johnson mandated that all computers purchased by the United States federal government support ASCII, stating, "I have also approved recommendations of the Secretary of Commerce regarding standards for recording the standard code for information interchange on magnetic tapes and paper tapes when they are used in computer operations. All computers and related equipment configurations brought into the federal government inventory on and after July 1, 1969, must have the capability to use the standard code for information interchange and the formats prescribed by the magnetic tape and paper tape standards when these media are used." ASCII was the most common character encoding on the World Wide Web until December 2007, when UTF-8 encoding surpassed it. UTF-8 is backward compatible with ASCII. As computer technology spread throughout the world, different standards bodies and corporations developed many variations of ASCII to facilitate the expression of non-English languages that used Roman-based alphabets. One could class some of these variations as ASCII extensions, although some misuse that term to represent all variants, including those that do not preserve ASCII's character map in the 7-bit range. Furthermore, the ASCII extensions have also been mislabeled as ASCII. From early in its development, ASCII was intended to be just one of several national variants of an international character code standard. Other international standards bodies have ratified character encodings such as ISO 646 that are identical or nearly identical to ASCII, with extensions for characters outside the English alphabet and symbols used outside the United States, such as the symbol for the United Kingdom's pound sterling. Almost every country needed an adapted version of ASCII, since ASCII suited the needs of only the US and a few other countries. For example, Canada had its own version that supported French characters. Many other countries developed variants of ASCII to include non-English letters, currency symbols, etc. See also USCII. It would share most characters in common, but assign other locally useful characters to several code points reserved for national use. However, the 4 years that elapsed between the publication of ASCII 1963 and ISO's first acceptance of an international recommendation during 1967 caused ASCII's choices for the national use characters to seem to be de facto standards for the world, causing confusion and incompatibility once other countries did begin to make their own assignments to these code points. ISO/IEC 646, like ASCII, is a 7-bit character set. It does not make any additional codes available, so the same code points encoded different characters in different countries. Escape codes were defined to indicate which national variant applied to a piece of text, but they were rarely used, so it was often impossible to know what variant to work with and, therefore, which character a code represented, and in general, text processing systems could cope with only one variant anyway. Because the bracket and brace characters of ASCII were assigned to national use code points that were used for accented letters in other national variants of ISO/IEC 646, a German, French, or Swedish, etc. programmer using their national variant of ISO/IEC 646, rather than ASCII, had to write, and thus read, something such as instead of. C trigraphs were created to solve this problem for NCC, although their late introduction and inconsistent implementation in compilers limited their use. Many programmers kept their computers on ASCII, so plain text in Swedish, German etc. contained and similar variants in the middle of words, something those programmers got used to. For example, a Swedish programmer mailing another programmer asking if they should go for lunch, could get ensar as the answer, which should be na jag har smorgasar, meaning no, I've got sandwiches. Eventually, as 8, 16 and 32-bit computers began to replace 18 and 36-bit computers as the norm, it became common to use an 8-bit byte to store each character in memory, providing an opportunity for extended, 8-bit, relatives of ASCII. In most cases these developed as true extensions of ASCII, leaving the original character mapping intact, but adding additional character definitions after the first 128 characters. Encodings include ASCII, VICI. Although these encodings are sometimes referred to as ASCII, true ASCII is defined strictly only by the ANSI standard. Most early home computer systems developed their own 8-bit character sets containing line drawing and game glyphs, and often filled in some or all of the control characters from 0 to 31 with more graphics. Kpro CP/M computers used the upper 128 characters for the Greek alphabet. The Petsky code Commodore International used for their 8-bit systems is probably unique among post-1970 codes in being based on ASCII 1963, instead of the more common ASCII 1967, such as found on the ZX Spectrum computer. Atari 8-bit computers and Galaxija computers also used ASCII variants. The IBM PC defined code page 437, which replaced the control characters with graphic symbols such as smiley faces, and mapped additional graphic characters to the upper 128 positions. Operating systems such as DOS supported these code pages, and manufacturers of IBM PCs supported them in hardware. Digital Equipment Corporation developed the multinational character set for use in the popular VT220 terminal as one of the first extensions designed more for international languages than for block graphics. The Macintosh defined Mac OS Roman and PostScript also defined a set. Both of these contained both international letters and typographic punctuation marks instead of graphics, more like modern character sets. The ISO/IEC 8859 standard finally provided a standard that most systems copied. A popular further extension designed by Microsoft, Windows 1252, added the typographic punctuation marks needed for traditional text printing. ISO 8859-1, Windows 1252, and the original 7-bit ASCII were the most common character encodings until 2008 when UTF-8 became more common. ISO/IEC 4873 introduced 32 additional control codes defined in the 89F hexadecimal range, as part of extending the 7-bit ASCII encoding to become an 8-bit system. Unicode and the ISO/IEC 10646 universal character set have a much wider array of characters, and their various encoding forms have begun to supplant ISO/IEC 8859 and ASCII rapidly in many environments. While ASCII is limited to 128 characters, Unicode and the UCS support more characters by separating the concepts of unique identification and encoding. ASCII was incorporated into the Unicode character set as the first 128 symbols, so the 7-bit ASCII characters have the same numeric codes in both sets. This allows UTF-8 to be backward compatible with 7-bit ASCII, as a UTF-8 file containing only ASCII characters is identical to an ASCII file containing the same sequence of characters. Even more importantly, forward compatibility is ensured as software that recognizes only 7-bit ASCII characters as special and does not alter bytes with the highest bit set will preserve UTF-8 data unchanged. To allow backward compatibility, the 128 ASCII and 256 ISO 8859-1 characters are assigned Unicode/UCS code points that are the same as their codes in the earlier standards. Therefore, ASCII can be considered a 7-bit encoding scheme for a very small subset of Unicode/UCS, and ASCII is valid UTF-8.